Okay, let's see. Sarah B. No. Claire. Matt C. Luke. No, Stuart. Luke. Yeah. Okay. Yeah. Sorry. Jaden. Emma. Liza. Stuart. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Sean. Jules. Doa. Matthew. Colin. Emily. Rennick. Sarah T. And McKenna. Okay, let's see. Claire, I see. Kashal. Let's see who else came. Sarah B. Did Matt come in? Let's see. Olivia. Darwin. Colin. Rennick. Sarah T. No. Okay. All right. All right, time to get started. Okay, so here's what we were talking about last time. We were talking about path independence. And again, it's kind of a weird idea. It's almost outrageous to suggest that there could be a vector field for which the value of the line integral of that vector field it kind of doesn't depend on the curve. I mean, okay, yeah, a little bit. Now it depends on the endpoints, right? You have to fix the starting and end point and ending points. So that is but still you're only fixing two of the points. There's infinitely many points in the middle. You're saying, yeah, go crazy, go wherever you want, it doesn't matter. And again, it's at first glance, it strikes me as outrageous to think that this would even be possible. And again, here's kind of my thought process that here's a couple of line integrals. Sorry, stylus. A couple of line integrals starting in at the same point. And yeah, but they're totally different paths. And so it's not hard to see that, of course, you get totally different answers. And shouldn't this always be possible to screw up the value by just wiggling your curve over there a little bit? And it just seems like it ought to be able to, you ought to be able to mess it up. So anyway, with that, intuition taking us the wrong way, as it turns out. All the more surprising when it finds out that not only is this possible, it's actually pretty common. In fact, every gradient field has this feature. Let's see, what color am I using here? I forgot. Gradients are always path independent. Right, and easy to see why, because again, with the same starting and ending points, again, that's got to be fixed, right? If you have one curve, how are you going to compute the line integral? Well, you're going to compute it with the fundamental theorem of line integrals, which only depends on those two endpoints, the starting and ending points. And then another curve, well, you're going to compute it also with the fundamental theorem of line integrals, which has the same starting and ending points. And so you get the same value, right? So really, ultimately, not that surprising. It's still impressive, though, that not only are there some, but there are many vector fields that have this remarkable property that it doesn't matter which curve you use, just it only matters where the curves start and ends. Okay. All right. And then again, I wave my hands at the suggestion that, in fact, this goes both ways. Not only is every gradient path independent, but furthermore, every path independent is also gradient. So this is if and only if. And again, just as a reminder, I'm sweeping all issues of regularity under the rug. It's not what this course is really mainly about. Okay. Yeah. Oh, just for completeness, let me also throw out there, just so you know, cultural point maybe, but these regularity issues do make a huge difference. And there's a tremendous amount to say about which of these statements that I'm making continue to be true when you have regularity problems. If your vector field has a singularity, everything goes out the window that I'm talking about. There's whole new considerations you have to worry about. So again, it's too much for us to go into in this course. So these are not minor little formalities that can all be pounded out. No, there are changes. There's different results that happen when you have regularity issues, and it's just too much for this course. Yes.
What is your regularity issue?
Regularity means stuff like, is the vector field continuous or is it differentiable? Stuff like that. How nice is your function? Yeah. So stuff like that. Does that make sense?
If a vector field has a vertical line, would that mean it's not differentiable?
Differentiable is something you determine by looking at the algebra. All right, and so if all of the components of the vector field are differentiable, right? In other words, it means that you can, in this class, this is flashing back to chapter 4, but the way we determine differentiability is by determining continuous differentiability, which we determine by taking partial derivatives and just confirming that they're continuous. Yeah, so it's something. It's an algebraic condition. And so, yeah, how it looks is manifests in different ways. Yeah. Okay. Yes.
When you say a gradient field is path independent, do you say if I pick two random points in that field, it'll be path independent?
So path independent means two things. Well, there's a succession of things that have to be said. So if you pick any 2 points, and I don't care which 2 points you pick, and then with those 2 points picked, if you pick any 2 paths that start and end, they have the same starting point, right? And they have the same ending point, right? Then those 2 line integrals will be equal. That's what path independence means. So this works for any pair of points, A and B. And for a given pair of points, A and B, this has to work for every pair of curves corresponding to A and B. So it's a tremendously huge statement. Yeah. Right. Okay. Okay, so yeah, so then of course there's this other point of view that we can take on path independence. So this is just the innocent observation that if you have one curve going one way between a pair of points and another curve going the other way, then when you put them together, you can think of that as making a single curve kind of going all the way around, except of course you're going backwards. on the backside, if you will, right? The second half, you're going the opposite direction along C2. And so with this observation, saying that these two line integrals are equal, just subtract and note that what that means is it's the same as saying that going around that purple curve, going around the boundary, going around a closed curve, let's say it like that, that you get 0. So these are two different ways of saying the same thing. And some people prefer, there's something about, the phrase path independence that kind of suggests this language, because we're looking at two different paths, and what you get as a result is independent of which of those two paths you pick. Thus, path independent, right? It kind of fits with the terminology better. There's a point of view that says algebraically, it's a little easier to talk about just, hey, any closed curve, the line integral needs to be 0. A little bit more succinct, arguably. So anyway, neat to observe that these two different formulations, take your pick, they are the same. They're equivalent. Okay, yes?
And we're just talking about vector fields right now?
Yeah, that's right. So the word path independent, this word path independent, it always is in reference to a vector field. That's right. Yep. All right. Okay, so I think it's kind of fun to see a visual example of path independence. We talked about this last time, but this was, I believe, the last thing we did. Let's think about the altitude function, h being altitude, right? And as these people, hard to tell much about them, but anyway, these people walking around these stairs, they are walking along, and their altitude presumably is changing as they walk. Right, or at least that's the suggestion from the way it's drawn. And the way you keep track of how much their altitude is changing, of course, is by looking at the gradient of the altitude function. Well, it's a gradient, which means it's path independent, which we just got through arguing, means that all closed line integrals are 0. Well, this closed line integral is keeping track of how much the altitude is changing. Well, let's kind of look at the picture and see what's happening with this this group along the outside here. They're clearly walking uphill there. They're clearly walking uphill there. They're clearly continuing to walk uphill there, and then they continue to walk uphill there. The Escher drawing suggests that that closed line integral would be positive. Right, which, well, according to all gradients being path independent and et cetera, that's not possible. Can't be positive, has to be 0. So this is a sort of a mathematical way of addressing what I will admit is, of course, already perfectly obvious, right? If you walk around and you come back to the same place, you didn't gain any altitude. Right, so it was already obvious, but this is sort of the mathematical take on it. Or you could say that this is the kind of issue that path independence disallows. I saw a hand somewhere. Yeah.
And when you say a closed line integral, you just mean starting and ending at the same point.
Yep, that's exactly right. Closed. Let's see. I have closed curve means starting and ending at the same point, and a closed line integral means a line integral around a closed curve. That's right. And just for the record, this little notation here, and I put an arrow to point to it, when there's a little circle there around, around the middle of the integral symbol, that little circle is just a sort of a reminder indication to the reader that this is not just any line integral, but it's a closed line integral. Yeah, yes.
So what does it physically represent when you take the integral of a vector field dotted with the dx vector?
Well, so there's different points of view on that, right? So I mean, if the vector field represents if the vector field represents forces, then the line integral represents work.
So in this case, with the stairs,
Well, in this
like,
case,
they weren't
yeah,
Escher stairs and they were just like a regular stairs?
right. Then notice we've got a gradient dot a displacement, right? Gradient is a way of keeping track of how you relate input changes to output changes. So I have a gradient and I'm dotting it with an input change. And so what it gives you is the output change. It's telling you
So there's a change in altitude.
total change in altitude along whatever your curve is. That's right. Integral of the gradient of the altitude function always gives you the change in altitude.
So because there's a change of 0 with the Escher stairs.
Yeah.
We're saying it.
Well, there should be a change of 0. Escher's trying to con us into believing that there is a change of more than 0. And this is how we, mathematically prove Escher is lying.
So does
Yeah.
0 mean that there's a change in altitude of 0 at every point, or just when you
So-
start at one point?
No,
and walk
this-
around?
So what this is saying is that this closed line integral is 0. And just for the record, there is no such thing as change at a single point. Right? There's a process of changing, but no one could make such an, we're not saying that functions don't change at all, ever, right? We're just saying that when you walk around, look, go for a walk on campus, you're clearly walking uphill sometimes. But if you go for a walk and then come back to the point that you ended, the amount that you walked uphill, the amount that you walked downhill, it's the same because you came back to the same point. Yeah, right. Cool. Is everybody happy? All righty, so let's move it along. So here's a computational example, and I'm going to point out before I do this computational example that's not really the point of path independence. Why don't I throw this out there? So y'all may recall that I was making fun of the physics convention to use yet another word to describe these vector fields, gradients, namely. That gradient, being a gradient already says something, and in fact, the word gradient tells you what the concept means. That's a great word, right? Conservative is, I don't know what that means. I mean, I do, but I'm just saying that the word itself does not suggest what it means, right? Path independent. Another great term, the term itself is telling you what path independence means, which is great. So then there's this term conservative, and it's unnecessary, throwing out additional words that we just don't need. Okay. But let me tell you where it comes from. Roughly speaking, again, it comes from physics. It comes from the idea of conservation of energy. Conservation of energy requires the notion of potential energy. And I claim that there being a notion of potential energy for a given force field requires, you think about it, that I be able to talk about what that potential energy is at points, or at least in comparison between two different points. Like if I know what the potential energy is here, I need to be able to talk also about, respectively, what is the potential energy here? What is the difference between two values of potential energy? Well, it's how much work does it take to get from there to there. For that to make any sense at all, that amount of work has to be well defined. It has to be the same no matter which path you take. So specifically, path independence, the way I see it anyway, path independence is the feature of vector fields that you need to be even able to define the notion of potential energy in the first place, right? So path independence is a really valuable conceptual tool. Without path independence, it's really kind of hard to make sense of the idea of potential energy, right down to it. Right. So that's, I think, what potential energy, what path independence is good for. Not very often is it useful for computation. And let me show you why. If you know that your vector field is path independent and you're going to use that in your computation, well, guess what? Being path independent, it's also a gradient. Being a gradient, you can use the fundamental theorem of line integrals, which is a sledgehammer for computing line integrals. So in some sense, why do I need a tool to compute line integrals for this special category of vector fields when I already have an awesome tool for computing line integrals of this special category of vector fields? Right? It's computationally, I don't want to say who cares, because there are some rare exceptions, and I'm going to show you one. But Anyway, it's not the primary point of path independence. Okay. All right, so example, here's a path independent vector field. I'll let you know in a minute how I know it's path independent. For the moment, I'm going to sweep that under the rug. Path independent vector field, and I have a curve as the top half of the unit circle oriented clockwise. I have there, and let's compute this line integral. Okay. All right. Well, now the vector field is given to be path independent. And that means that even though the path has been given, path independence is on the table. And so really all I have to do is get from A to B. And how I get from A to B, free choice of mine. Vector field's path independent. I can choose any path I like. And I tell you what, I don't like that path. It's all curvy and stuff, and it's going to involve trig. And I don't like trig, all else being equal. Right? I mean, if X and Y are sines and cosines and such, then my integral is going to have sine squared and cosine cubed. And I mean, it's not that I can't do those integrals, but they're kind of a pain. So I'm going to say fooey on that curve. I don't need that curve. All I really need is the starting and ending points. And now we can pick whatever curve we want. And if we want to pick that path there, we are free to do so. I advise that we don't. Let's make our lives easier, not harder. And so I'm going to pick, of course, and I suggest you also pick the easiest path, right? Almost always the straight line path between the 2 points. Easy to parameterize. And if you want to plug and chug with that path, you can. Now, in this case, it works out even better. Not only can I just explicitly plug and chug, but in some sense, I don't even really have to, because check it out. As I move along this curve, notice y is never changing. That means that dy is 0, which is pretty sweet. Notice furthermore now that in this path, not only is y never changing, y itself is always 0, which means that this first component of the vector field always 0. So in some sense, I don't really have to crank out a bunch of details. Everything disappears in a puff of smoke here. And I'm adding up a bunch of zeros, and that adds up to 0. And we're done. Everybody see what happened? And so we use path independence here to turn the question that was given, which would have been, annoying and hard. Let's see here. So again, the path that was given, that path, we use the path independence to say, I don't like that path. I'd much prefer to use this path where life is good, and then good things happen, and we win. What do you think? Yes?
The property of using the path independence doesn't necessarily mean it's always 0, or it
Oh, certainly not. No. Yeah, now around a closed curve, it would be 0, but notice that this is not a closed curve, right? So this path that we were given does not start and end at the same point, and so yeah, you won't always get 0. In fact, I don't want to say rare to get 0. The world's full of lucky breaks and symmetries. And not only that, I like the lucky breaks and the symmetries. And for whatever it's worth, you're going to notice that disproportionately often the answer to questions like this will happen to be 0. Right. Yeah, it's not, it does not have to be 0. Okay, now that said, let me point out this example is on, this example is not really a counter argument to my suggestion that computationally path independence is limited value. Because here's another thing you could have done. You could have said, oh, you're giving me a path independent vector field. Oh, thanks for the tip. That means it's a gradient. I could just try to find the antigrade. Oh, you know what? I think I can eyeball the antigrade. Oh my God, is the antigrade, is it x squared y? Oh my gosh, look at that. I'm just going to use the antigradient x squared y, fundamental theorem of line integrals. Bam. Right? So arguably that would be the easier approach here. So What I could have done though, and didn't because I wanted to spare us all the computational inconvenience, is there are plenty of vector fields where it would be very hard to find the antigradient. And yet path independence is easier to identify sometimes. Right. So I didn't want it's great big ugly vector fields that I didn't want to weigh us down with. Okay. So I'm going to say morally this example stands as a sometimes useful tool for path independence. Okay, so how do we know when a vector field is a gradient? What's the giveaway? You know, gradient, path independent. Of course, gradient, path independent are the same thing. So there is a neat test. It's a very clever observation. In fact, let me go ahead and circle on here that in this argument I'm about to show you, the first 3 steps we've already observed, right? We've already observed that if you have a gradient, that means it's path independent, and being path independent means closed line integrals are always 0. So that we're halfway done just by writing down stuff we already knew. So the slick move, the tricky little move that gives us a very convenient computational test is to just cite Green's theorem. Keep in mind, Green's theorem says that closed line integrals can be computed as a double integral of Green's operator over the interior. Right, everybody remembers Green's theorem from 6.2. So that having been observed, let's kind of continue the argument. Okay, so we know we got a vector field, it's a gradient, therefore it's path independent, therefore this closed line integral is always 0. Okay, well that means that this double integral is always 0. And now I just kind of appeal to your kind of, I'm going to call it algebraic sense, but what function could it be, right? What could this integrand be if no matter what domain you pick, the double integral is always 0, right? All double integrals of it over here, any big region, small region, whatever, any domain that you give it, the integral is always 0. I claim that there's only one way for that to happen, and that is that the integrand itself has to be 0. What do you think about that? Everybody happy with that? Yes.
So we're not saying we went directly from F equals gradient of F.
No. Yeah. So
We're saying
this is my statement and this is my argument.
Okay.
Yeah. But having made this argument, having done the whole argument, the result is that now I know that this statement is true, and this is the neat punchline. If you want to ask, for example, hey, I got a vector field, I'd like to know if there's an antigradient. I don't want to be going on a wild goose chase trying to find the antigradient if there in fact is no antigradient. So how can I spare myself this endless, fruitless search for the thing that doesn't exist? Oh, okay, well, you can do this one thing, compute Green's operator. If you get 0, then you're good to go. If Green's operator is 0, there is an antigradient. So go out and find it. And vice versa. If you compute Green's operator and you don't get 0, game over. Don't even try to find the antigradient because there is no antigradient to be found. Yes.
So is this a test we would use for non-vector fields?
No, this is only about vector fields. Yeah, so we're talking about vector line integrals of vector fields. Yeah.
Oh, I'm sorry. I mean vector fields that we don't know if they're gradients or not.
Yeah, that's exactly the point. Yeah. So if you're given some vector, like up here, I told you this was a path independent vector field, but if I hadn't told you that, if I had just said, hey, here's a vector field, right? Yep. And in fact, just as an easy example, we'd take the x partial of this, which is 2x. Then we subtract the y partial of that, which is 2x. And we sure enough get 0, which means it is a gradient, which means that it is path independent. Is that cool?
That's what it is.
Yeah, yeah. So yeah, it's a slick move. Neat fact to know about. Green's operator, simply looking to see whether it's zero or not zero, will tell you whether or not to waste your time trying to find an anti-gradient. And by the way, I recognize I still haven't told you how to find anti-gradients, and I will do that. That's one of my next things. It's coming up real soon. Okay, real quick though, I want to talk about language a little bit. I'm going to point out that we now have a third very reasonable, very communicative, very geometrically substantial choice of words to describe these special vector fields we've been talking about. So gradient, we already talked about. That's very helpful. That word communicates exactly this very important feature of such vector fields, that they are literally gradients. It communicates algebraic information. Path independent communicates, I think, very well this this kind of weird feature about, hey, check it out, you can use any different, as long as you preserve the endpoints of the line integral is always the same. Path independent really says that, right? So here's the third, what I think is a really great term that communicates good information about exactly the same vector fields, and that is irrotational. And well, where does that come from? Irrotational comes from the fact that you got to keep in mind, what does Green's operator measure, right? And I'll refer you back to section 6.2, but Green's operator is measuring to what extent does your vector field represent a fluid that's got a kind of a sort of a rotational aspect to it, that if you were to drop a leaf onto the flowing river that is described by your vector field, Green's operator tells you, is it twisting as it flows, or is it just moving around and keeping its orientation like this, right? So that twisting aspect of the field is what Green's operator measures. It measures how much rotational there is in the field. And so if that is zero, then irrotational is a pretty good choice of words. Everybody see what I mean there? Yes.
Is that circulation? Is that the-
Yeah, circulation. I like to think of it as circulation density, but yeah, absolutely. So I think this is a great choice of words too, and because it communicates explicitly something, an important feature that this vector field has, just like these others. So irrotational, gradient, path independent. These describe important concepts. And given that we have three excellent words describing important features of these vector fields, I just don't feel like we need a fourth, which is conservative. Which, anyway, there's my complaint about the terminology. But anyway, heads up, again, conservative, very common in usage. Okay, there's a similar fact in 3 dimensions. We've been looking at vector fields in 2 dimensions, but if your vector field is in 3 dimensions, then instead of Green's operator, it's the curl, as it turns out. And now we haven't yet covered the theorem that's going to allow us to address that. Notice we needed to use Green's theorem here in order to make this connection, right? We needed Green's theorem. Well, there's a theorem that we need to make this connection. We haven't done it yet. So this is going to have to wait, but just as a heads up, and you can use this result now, that's fine. If you have a 3-dimensional field and you want to know, is it a gradient? Take the curl. If you get the 0 vector, then you're good. And if you don't get the 0 vector, then there is no anti-gradient. And again, don't waste your time. Okay, so proof of that, again, to come later, section 7.3. Okay, so let's see a quick application of this. In fact, I'll leave this on the screen. So here's a vector field. I want to ask, reasonable question, is this a gradient? In other words, should I try to find the anti-gradient? Right, and I'm going to resolve that by computing the curl, and let's see what I get. Right, so computing the curl. Now, remember, curl is this weird formula, but by the way, make sure you know, I know there's a bunch of weird formulas in this class, but that's one you got to make sure you know. And the very first thing that you write down when you compute the curl of this is that we're going to take the y partial of that, which is 2yz plus 1. And then we're going to subtract the z partial of that, which is 2yz. And again, you look back, find the formula in chapter 3, make sure you memorize that formula. And then we can proceed. But oh, wait a minute. You know what? In fact, we don't even have to. In fact, we're already done, because the curl, whatever it ends up being, I don't even really care what these components end up being. I already can tell that there's no way that this is going to be 0, right? Oh, I ran out of colors. Do I get 0? Clearly not. The first component's not 0. There's nothing the second and third components could be that could possibly change the fact the first component's not 0. And since that first component is not 0, then the curl is not 0. And therefore, there's no anti-gradient, and computation over. Everybody see what I mean there? It's a neat little trick. And by the way, you can kind of do this sort of thing in your head. And once you're comfortable with the formula for curl, you have that fully memorized, because you can just kind of eyeball and be like, all right, is the y partial of that equal to the z partial of that? Well, let's see, the y partial, the z partial. Nope. And eyeball check. Sometimes you get lucky. Now, had this been 0, then yeah, I would have to go through and keep confirming, because keep in mind, in order for the 0 vector to be the 0 vector, all 3 of the coordinates have to be 0. But to be non-zero, all you need is any coordinate not to be 0. Okay. All righty. So let's see here. What I want to do now is show you. Oh gosh, let me lead into this a certain way. So you may recall when we saw. Well, you know what? I'm getting ahead of myself. Okay, so I have made vague allusions so far to there being this more sophisticated take on this material than I can give in this course. It just, it doesn't really, it's a little too much for what would be reasonable here. And that's differential forms. And there are certain things that you can do with differential forms and ways that you can set things up that make it's clunky and mechanical and counterintuitive and yet bonkers powerful. And we're not going to do that in Math 219. If you're curious, check out chapter 8 in the textbook. They do a whole bunch of good stuff there with differential forms. But again, not required, and I'm not expecting you to do that. What I do want to do is give you kind of the, without using any of the rigor or any of the scary aspect of chapter 8, I want to break it down to what I'm going to call a pattern, right? There's a certain diagram that I've drawn here. I'll call this the strategic diagram for R2. And it just makes a lot of neat things visually apparent, or not. It makes a lot of neat patterns appear that help you remember a lot of the results that we're talking about. So what we do to make this diagram. So to finish the lead in, roughly speaking, this is a watered down, boiled down, what you need to know, how to be useful in the context of Math 219 version of differential forms. Okay, so roughly speaking, notice how when you take a gradient of a function, you get a vector field. Notice how when you take Green's operator of a vector field, you get a function. So what I'm going to do here, for reasons that are deep, I'm going to compose these two operators. And something really great happens, and that's this exactness that we talked about back in chapter 3. I talked about the exactness of, it was the 3-dimensional version of this, but we talked about exactness, which means everything has a lifetime of 2. And notice that's kind of what we just got through talking about. If you have a function and you take its gradient And that gives you a vector. If you take that gradient vector field, compute Green's operator, you get 0. Lifetime of 2. If you have a vector field and you take Green's operator and you get not 0, could there be a function whose gradient is the original vector field? No, because if there were such a function, then this would be a lifetime of 3. We know there cannot be lifetimes of 3, so therefore, no, there is no. This is where this story starts. This is the lifetime of 2, and there's no anti-gradient. So it's all on the diagram in some senses. This looking at this composition and remembering that everything has a lifetime of 2. Okay, so I find that to be, as a memory tool, I find that to be satisfying because it's a visually apparent. I can play a little visual game instead of trying to remember. Wait a minute, which way does it go, and things like that. Okay. All right. Now, for whatever it's worth, I'll point out that you can do the same thing for domains. So if you have a 2-dimensional region, you can talk about the boundary of a 2-dimensional region and you get a curve. But also, if you have a curve, you can talk about taking the boundary of that curve, and that gives you a pair of points. And here's the weird thing. This is, I'm going to call approximately exact also. And I have to say, I have to put the little air quotes or a little tilde there, because there is a little minor issue of formality here to make this a actually true statement, and I don't want to get bogged down in the formalities. If you're curious about this asterisk, approximation statement there, come talk to me in office hours. I'll be happy to explain. But we roughly speaking, you don't need to worry about that. And so let me point out, just to explain the claim that I'm making here. If you have a region and you take its boundary curve, guess what? That curve starts and ends at the same point, or said differently, that curve has no boundary. It doesn't start or end really anywhere. It's a closed curve, right? So there's kind of a lifetime of 2, kind of going the other direction. See what I'm saying? And then likewise, suppose you have a curve, and suppose you take the boundary, and suppose that, so I'm going to draw a picture of my curve here. So suppose that your boundary is not 0, right? So you suppose your boundary actually is a pair of points. There's where it starts, there's where it ends in 2 seconds. Could such a curve be a boundary of something? Well, no, it's not a closed curve. This is a fence that doesn't close up. You cannot pen in any cows inside of that fence because it's open. Right. So again, lifetime of 2, right? When the boundary of a curve is not 0, that curve cannot be itself the boundary of a region. Yeah, you had a question.
Yeah, I was wondering, what does it really mean though to take we have curves to points? Is that what you're talking about?
Yeah.
Right now?
So yeah, that's right. So given a curve, the boundary just means the endpoints.
Oh,
The endpoint, yeah. So the starting point and the ending point. Yeah, what we call them both the endpoints. Yeah, right. Yeah. So anyway, it's kind of you put it into a little diagram like this, and there's natural connections there. I also like to point out, and I think that this is a really valuable fact. We've seen 2 theorems recently. We've seen the fundamental theorem of line integrals. We have seen Green's theorem. They talk about 2 totally different things. One's talking about measuring circulation. Right. The other one's talking about accumulation of change. Circulation and change are very, very different things. And yet, if you think about it, look in the context of this diagram, what they say is shockingly similar pattern. So let's take the fundamental theorem of line integrals, for example. Fundamental theorem of line integral says if you have a function and you look at its gradient, now let me, so you got a function, you're going to look at then the gradient of that function. If you have a curve and if you look at the two boundary points of that curve, then the line integral of that curve over that curve of the gradient field and the change of that function between those 2 points, same. Now, okay, so there's a little diagrammatic pattern there. Now let me point out this is the exact same pattern over here for the for Green's theorem. And just to be dramatic about it, I'm going to highlight like this. And I'm going to slide this over here, and my layout didn't quite work out. So I'm going to have to redraw the diagram. But this is the pattern here. And just so things will fit better, let me redraw. If you have a vector field, sorry, hit the wrong button. If you have a vector field and you compute Green's operator, if you have a two-dimensional region and you look at its boundary curve, then the double integral over that region of the Green's operator function is equal to the circulation around that boundary curve of the original vector field. Same exact pattern. Everybody see what I mean? And if you look at these theorems if you look at them in different contexts, you'd be forgiven for not noticing that, well, they're really similar theorems because they don't look really similar, right? Green's theorem is about circulation. Fundamental theorem of line integrals about change. They're totally different takes on, they connect to line integrals, I suppose, but they're completely different points of view on how to compute line integrals. And they just don't look the same at all. But when you draw the diagram this way, you see, oh my gosh, it's the exact same pattern. It just sort of slid over sort of one notch. So I think it's really interesting. By the way, just so you know, why is there this pattern? How could these two theorems have so much in common? It's because they're both theorems in fact, they're both special cases of the same generalized theorem. There is a single theorem in the language of differential forms that both of these are special cases of. So, all right, neat fact. All right. So I also like to point out that you can see the equation of these three concepts, right? Gradient, path independent, irrotational, all describing the same thing. You can kind of draw a picture. Being a gradient means that you're talking about a vector field that, well, there it is a gradient of something. Being irrotational means that when you compute Green's operator, you get 0. And being path independent means that whenever you have two curves with the same endpoints, then they will give you the same value for the line integral. So it's just kind of, again, I find it satisfying. Maybe just because I'm a visual kind of person, right? I like to see things as opposed to having them be abstract. But I find this very satisfying to see on the diagram, okay, these three different ideas, these three different concepts, this is what they look like. And they're all talking about the exact same vector fields, I emphasize. All of these are the exact same vector fields that have all three of these properties. And this is what those properties look like on the diagram. Okay. Okay, so last point that I want you to consider about this diagram. Let me see, let me zoom out. Oh gosh, I've got a lot to erase here. Let me do that. Okay. So suppose you want to compute a line integral. The diagram kind of suggests some ideas for things that you might want to try. So the line integral could be part of, maybe I can use the fundamental theorem of line integrals. Maybe I can use Green's theorem, not sure. The diagram kind of helps you figure out what to ask to decide whether you can use those theorems and how to decide if you're going to use those theorems. So for example, let's ask, can I use the fundamental theorem of line integrals? Well, the diagram tells me, look, whatever your curve is, you're going to need to take the boundary of it. Cool. That's not a problem. But it also tells me whatever my vector field is, I'm going to need for that to be a gradient of something. It's literally asking me, literally is a strong word, but it's almost explicitly asking me, hey, is your vector field a gradient? And then it's also suggesting, oh yeah, don't forget about the exactness. The way you're going to decide if it's a gradient is by computing Green's operator and seeing if you get 0. Right, so the diagram does that work for me. It is telling me, here's what you need to know and here's how you find it out. Right, I think that's cool. And by the way, it does the same for thinking about using Green's theorem. Right, so if you've got, again, a line integral here and you want to know, can I use Green's theorem? Well, whatever my vector field is, I'm going to need to compute Green's operator. Fine, that's no problem. Whatever vector field you give me, I can compute Green's operator. It's just a couple of partial derivatives. That's not a question. But it also points out, hey, your curve, I'm going to need that to be the boundary of some region. Is your curve the boundary of some region? Thank you, diagram, right? Again, it's pointing out what I need to check. It's also, again, telling me how to decide, and that is my curve can't have endpoints, right? Boundary's got to be 0. If you want to have what you might call an anti-boundary, it's another term that I'm trying to popularize. If you want to have an anti-boundary, then its boundary had better be 0. So said differently, it's got to be a closed curve. And so you can just look at your curve and see, is it a closed curve or not? Okay. All righty. Okay, let's see. We've got 1 minute. I guess we don't have time to start a new page. Let's just draw the line right there. But you can see the next thing that's coming up real soon here is how to find anti-gradients. We'll get to that on Friday. See y'all later. Have a good one. Oh my gosh. Okay.
Thank you.
Yeah, no worries. Yeah.